Okay, so it's 6 p.m. and the class and the timing for the live session is from 6 to 8 on February 18. So that's today. So I will wait for a couple of minutes and see if people join. Otherwise, I will start the session and I'll do the recording. Okay, and upload. I'm waiting for a couple of minutes and see so that people can join. I will wait till 6:05 p.m. After that, I will start. Okay, it's already 6:05. I will start the session. People can join in between also. So, hello everyone. Welcome to the live session for the course Sensors and Actuators. So, this is week 4. Yeah. So, let me introduce myself first. I am Ananya, a PhD scholar in the Department of Electrical Engineering, IIT Kanpur. My specialization is microelectronics and VLSI, and I work on mainly on fabrication of thin film and different oxide material and semiconductor devices. So I will start the session now. As always, I will start the session with a brief overview of the topics those were covered in this week. The idea is that this is just to give you an overview. I'm assuming that all of you have watched the lecture videos along with the lab classes. So I'll just give you an overview, not go into the details of all the topics. So this is week 4. So in this week, the topics those were discussed mainly a few examples of MEMS based sensor. Those are used for biomedical applications were given, and there were few lab classes. Okay, I think someone joined. Okay, I just started the session. I hope I am audible and you can see my screen. I'll just start the session now. Okay, again, I am Ananya. I will be your TA for this session. So I conduct the session on every Tuesday from 6 to 8, and this is week 4 for the course Sensors and Actuators. Okay. Okay, if you can if there is any problem with my audio and video, please let me know. You can unmute and speak. Okay. Okay, thank you. Thanks for the confirmation. So I will start with the topics those were covered in this week. So uh, I will give you a brief overview. I hope that you have watched the lecture videos, and there are few lab classes also in this week. So I'll mainly cover the lecture videos because the lab classes are self-explanatory, and this is mainly a tutorial session. So these live sessions are mainly to ask question and solve questions. So I'll not focus on the lab part, but I'll give you a brief overview and maybe few questions based on those lab classes. Okay. So in this week, the what topics were covered. So in this week, some examples of MEMS sensors for biomedical applications were given. So when we talk about MEMS sensor for biomedical application, so if you are making a sensor, a MEMS sensor for biomedical application, so basically it has two components. So that will be a design of the sensor, because that is also very important. You want to design your sensor for sensing a particular bioanalyte. So that should show good selectivity, sensitivity, and all other parameters, like those we use to characterize a sensor. All those parameters, ideally we want everything to be very good, but then again there will be some compromises, some trade-offs between different sensor characteristics. Okay, so it has two different components. First part is the design, and second part is fabrication. Okay. Now, why both of these very important? Design, you know that you want to design a sensor which is very sensitive, which is very precise and accurate. Fabrication is also very important because we are talking about MEMS sensor. So these sensors will be in micro and nano dimensions, and there will be some like different types of structures like cantilever, diaphragm, suspended beam. So and all of those in a very small dimension that we cannot even see directly from our eyes. So we need a microscope, we need other kind of like characterization techniques to actually see those structures. So that is why the fabrication is also important, because like it is not always easy to make those structures very precisely with certain dimensions. Okay, so sometimes you need to go back and forth between the design and fabrication. So you will design and fabricate maybe this, then after fabrication you will go for testing and verification. Then you will see that okay, this is not working, maybe due to design error or maybe due to fabrication error. So if your purpose is not solved, you cannot use it for like application, then you will move again from fabrication to design. You will change your design, improve your design, and then go for fabrication, so that you can minimize fabrication error. Okay, so this is like can be like a hit and trial process, but not a random process. You will like you will analyze the error, what are the errors, and you will try to improve based on that analysis. Okay, now what examples were given in the class for MEMS sensor which are used for biomedical applications? So the examples were given was drug screening devices. So those are used to like determine which drug is efficient for a particular patient or a particular disease. So this kind of sensors can be designed for biomedical application, like using MEMS technology. Okay, so drug screening devices, that was one example given. And another example was drug delivery. So this example was not discussed like in detail, but this is again that it's kind of similar. Drug delivery is like you want to like deliver that drug precisely into that position. So for that, many small devices, small sensors and actuators are used for precise drug delivery. So this sensors and actuators will be in micro and nano dimensions. So these are very small, so that the efficiency of the drug, or the like it will be like targeted delivery, so that it can kill a particular something. So basically like that. So many works are going on in this category also. If you are interested, then you can look. Okay, so these are the two different aspects of MEMS sensor for biomedical MEMS sensor for biomedical applications. Okay, and two main areas where these sensors are used in biomedical application. Okay, now one thing you should consider in mind, that if you are designing a MEMS sensor for biomedical application or any sensor for biomedical application, precision is very important, because so you cannot compromise with the precision of these sensors, uh, because these are for medical purposes. So your sensor has to be very precise and accurate. Okay, so it usually involves a lot of research and design in fabrication and in testing and verification. So it is always not easy to directly test those sensors. So you maybe you will need some medical clearance from certain people. Your sample size for testing may be limited also, but it is very important, and this testing and verification part is done extensively, so that the sensors can be actually used for practical purposes. Okay, I'll make a note here. So precision is very, very important for biomedical application. And it involves extensive design, fabrication, testing, and calibration. So you know what is calibration. Calibration is basically that uh, so that you know what for what input we will get what output. So we are getting some output from the sensor. What is the expected input? Suppose it is a temperature sensor, which is say resistive. It's not biomedical application, I'm just giving an example what calibration means. That suppose you have a temperature sensor that will when temperature increases, the resistance of the material increases, the material that is being used in the sensor. So suppose a change in resistance delta R, that will indicate a change in temperature from say some reference temperature 100 degrees Celsius to another temperature T1, say 110. So this relation you already know, that if delta R is this amount, then delta T is will be this amount. So that is what calibration means. Okay, so when you design a sensor, that the input output relation, to know, you should know that input output relation precisely. So over the time, if there is any drift in your sensor, that is also needs to be calibrated properly. So that is what calibration means. It involves extensive design, fabrication, testing, and calibration steps, and this is very important for biomedical applications. Okay, so there were few examples given for MEMS sensor for biomedical applications. So the first example was pressure sensor. Okay, so before going to the pressure sensor, so there will be two steps like design and fabrication, as I mentioned earlier. So before going to design, you should know what is the working mechanism of a pressure sensor. So the example that was given, that was a piezo resistive pressure sensor. Okay, so what is piezo resistivity means? Piezoresistivity means that piezoresistive materials are those materials where the resistance of the material changes due to the applied force or pressure. Okay, so that is the working mechanism. So you need a material that where the resistance will change uh, due to the application of force and pressure. Now what are those material? One example that was discussed, that was given, is boron doped silicon. So silicon is a piezoresistive material, and with boron doping, actually the piezoresistive, not electric, piezoresistive effect actually increases. Okay, so boron doped silicon is a piezoresistive material. Now so that is what is the design part. So you know that you want to make a structure with a piezoresistive material, and you want to make it in a suspended structure because it's a MEMS sensor and you want to sense pressure. Now what will be the fabrication part? So in design part, it is also included at what will be the dimension of this piezoresistive sensor, what will be the thickness of the piezoresistive material. Okay, all of those things will come in the design part, and in fabrication, how will fabricate, that was discussed. in the class. So you will start with a silicon substrate, and there will be a SiO2 layer on top. Okay, so this is SiO2. Even if you keep silicon like outside, there will be formation of a small SiO2 layer itself, like due to oxidation in normal environment. Okay, but this is like the SiO2 layer on a silicon substrate. Okay, now then there are two processes to make a piezoresistive sensor. So the final design may be similar, but the steps are like the sequence of the steps are different. So in the first process, what you will do, so you will, this is your silicon and SiO2 layer. I will not write again, the diagram will be very difficult to read otherwise. And then you will coat, you will do a deposition of some piezoresistive material. Okay, now how you can do deposition, that we have already discussed in earlier weeks. So you do the deposition using some deposition techniques, either chemical or physical. Okay, or what you can do, you can do like a lithography on top of SiO2 layer, and you can use the you can do the etching of SiO2 layer, make an opening like this. Okay, your backside SiO2 will be same, then you made an opening of SiO2 here. Okay, next what you can do after this step, you can do like you can go for lithography and patterning and etching. So finally, what kind of, we have already discussed about patterning, lithography and etching in earlier classes, so I'll not discuss again. So final structure will be, you will have, not the final structure, but the next structure will be, you will have like this piezoresistive material on top of your SiO2 layer. Or you can go for doping. If you remember, I discussed briefly in earlier weeks that in microfabrication techniques, basically there are four components. One is deposition, where you, by which, using which you can make a thin film. Okay, that is deposition. And you can go for patterning, that is by using photolithography, and you can do etching, or by using lithography and etching you can make different patterns. And the last component is doping. So what you will do, as I mentioned, that boron doped silicon is a piezoresistive material, so you can dope this portion, like dope the silicon with boron, and because you have made a window here using SiO2, so doping will only be here in this portion, below the opening. So your structure will be something like this. This is the SiO2 layer, and this is the SiO2 window, SiO2 pattern that you have made using lithography, and there will be boron doped region here. Okay, it can be other kind of doping also, because boron was discussed and it shows very good photoresistive effect. That is why I'm mentioning here. So you do the doping, and also what you do another step of lithography. So as you can see that you did one lithography and etching, all of those steps to make a pattern like this. Then you did do doping, and then also do another lithography to make the electrodes here, so that you can make a connection from this piezoresistive material. Okay, so this is the electrodes. So this is after that, what you will do, you will go for bulk micro machining to make a suspended structure. And how we can do bulk micro machining, that is also we have discussed earlier. So this will be bulk micro machining. I'm not writing the full form here, you will already know this. So the final structure will be something like this. You will have a suspended silicon structure. Okay, so my diagram is not that good, but you so these are the piezoresistive material where you apply the pressure and you can measure the resistance. So there needs to be some contact or some probes by which we will measure the resistance. Okay, and for this structure, the final structure will be after bulk micro machining. So you will have again this kind of silicon structure. These are piezoresistive material part, and these are contacts. You will be able to measure resistance from this. Is there any question? Okay, so you can see here we have made it like a suspended structure with this kind of structure using bulk micro machining. So why we need that for pressure sensor basically? Can anyone answer? So we need this kind of suspended structure in case of to measure pressure basically, so that when we apply pressure, so if this diaphragm actually bends, so that will increase the sensitivity of the sensor. Okay, if it is rigid and stiff, then we will not be able to like the sensitivity of a pressure sensor will be low. Okay. Okay. Any question till now? If you can tell me if I'm going too slow or too fast. Okay. Uh, the next example that was given was example 2 was cell based screening. Okay, again before designing and going for fabrication, we will ask ourselves a question that how we can make the sensor. Okay, so what is the basic principle that was discussed in the class? Basic principle for this kind of sensor is the cancer cells will have different impedance, and if we apply different drugs on those cells, so that will react differently or behave differently. And what is this behavior? Basically we are measuring the impedance. Okay, so basically the impedance of the cells will change. Okay, impedance of the cancer cells will be different. Due to the application of different drugs. So the key point here is that the impedance of the cells will change. So what we need a impedance sensor. So you already know what is an impedance analyzer, what is actually impedance. So basically it is like a resistance. So we want to make a impedance sensor. Now see, there are a few questions you have to ask yourself, and then should go for design of this kind of sensor. So what question can be for especially for this example? So one question will be like, what is the range of the impedance? Okay, so we know that after application of the drug, the impedance of the cells will change, but how much? Okay, so you need a sensor, you need to make a sensor that will be actually sensitive to that much change. Okay, so the resolution should be uh, like higher. Basically the sensitivity of the sensor should be higher compared to the change in the impedance. Okay. Okay, sorry. Next question will be how you can measure. Suppose if you can remember in the lab class for impedance analyzer, there will be few specification for the analyzer. Okay, now suppose you, if you are designing a sensor, and it can say it, there is some change in the impedance. Okay, but you don't have a measurement system uh, using which you can actually measure and actually determine that say that this drug is effective for this kind of disease. uh, Unless you don't have the analyzer, it will not be possible. So how you can measure it also a valid question, especially when you are designing a sensor in a lab environment and you are testing it in a lab environment. If so in certain cases, like if you don't have the facility, so there will be some facilities available to measure those sensor. If your sensor is actually sensitive, but because of the measurement system you are not able to measure it, then you should find an alternative that where you can actually go for this measurement. Okay, so these are the questions we will ask before designing the sensor. Basically, this is the designing part, that we are designing the sensor to be as it should have a very good sensitivity, as high sensitivity as we can design, and then we will have a very good measurement system, so that even the slight change in the impedance we will be able to measure and quantify. Okay, after these steps, next comes the fabrication of the sensor. Okay. Now how you can measure, so this is the design part and how we will design it. So we will design an impedance sensor, and how we can design an impedance sensor. So we will measure the impedance, we will make some interdigitated electrodes. Basically it is same, it is similar like a resistance, so we'll need two electrodes to measure, but we'll make an interdigitated electrode structure because that provides better sensitivity, and we will measure the impedance of our cells, of the cancer cells. Okay, now what are the fabrication steps? So as given in the given in the lecture video, so we will take a substrate. The example given was glass, and then you will coat your you will make the interdigitated electrode first. So this is to make the interdigitated electrode, you will need some metal. We often use chrome gold because it's like, you know that gold will not react with many things, like so it does not get oxidized easily. If you use other metal, that may deteriorate with time. Okay, so and then chromium, thin layer of chromium is to provide better adhesion with the substrate. After that, what you will do photolithography and etching to make the interdigitated electrode. So we have repeated the photolithography and etching the part, how what are the different steps in photolithography multiple times, so I'm not going into the details. And finally, what we'll have, you will have your substrate and you will have your patterned metal. So this is metal, which is chrome gold in our case, and this is the substrate, which is glass. And this is the side view, and the top view will be like this. So this is like a finger like structure, comb like structure, which is the interdigitated electrodes. Okay, so these okay, then on top of it you will make an SU8 well, so that you can place your cells inside as well and do the experiment. Okay, so first step is to make the interdigitated electrode, and then make the SU8 well, and then you can perform your experiment, and then you can go for testing, verification and calibration, those steps I have mentioned earlier. So these were the examples, those were given in the class. So any question? If there is any question, you can let me know. I'm taking a pause. Okay, no question. So next few topics were, so these were small topics, those were covered. I will give you few points to remember. So these this is just for your reference, like a note, so you can refer later. Okay, so the next, as I mentioned earlier, that what we do, we make SU8 wells. Basically the SU8 wells are used in case of biological sensing, or in case of biomedical sensors. So because many a times you will have some kind of liquid analyte, liquid sample, so you want to place it on top of something, so that is why generally a well is made, so you know what a well means. So this is SU8 well made with SU8 material, which is a polymer, and but the difference is that it is in a very small dimensions. Okay, so what is SU8? SU8 is basically a negative photoresist. It is widely used in case for lithography. uh, it is like very well known, how we can do lithography using SU8 on silicon. Okay, so and it's very stable. Like, you know what a negative photoresist is. After UV exposure, negative photoresist becomes hard. Okay, the exposed portion becomes hard. So SU8 becomes hard when UV is exposed, and it is very stable. Like, you cannot it does not move very easily. It will not be able to remove SU8 like very easily. Okay, there are techniques. So once you made some is SU8 structure, there are few techniques to remove SU8, but in general these are very stable. So this material after exposure is very stable. Also SU8 is transparent, so I have used SU8 in our lab, so it's transparent. With the, like, it's the consistency is like it flows very easily. So that, so it is, in some cases it is useful, because if you want to make some transparent microstructures, so SU8 can be used. So what is SU8? It is a negative photoresist, and it is transparent, that you can remember. Okay, and then what was discussed in the class, that how SU8 is used in lithography, what is the process flow. It is slightly different than the other photoresist. So you can look again, as I mentioned earlier, the photolithography steps are photoresist dependent. So based on the photoresist, your steps can be slightly different. The major steps are same, that you will coat the photoresist, you will go for baking, and then you will do the exposure and development. Those are like basic steps, but the parameters and the timings, those may vary. And for SU8, what are the different conditions that you can look. And in case of SU8, the soft bake temperature is 65 degree, and the duration depends on the thickness of the SU8 layer. Okay, I think there are a few questions on this, that is why I'm writing this here. You can also look the data sheet of SU8 photoresist, and you will find all the details. Now, how you will know what is the thickness of the SU8 layer? So if you look the data sheet of SU8 or any photoresist, so how you do the coating of the photoresist on top of your substrate. So you basically do spin coat. You place your sample in some vacuum chuck and you rotate at a very high speed, say 6000 or 8000 rpm, like rotation per minute. Okay, so now based on that rotation and based on the viscosity of the photoresist, so you will achieve certain thickness of photoresist on top of your substrate, and that is generally given in the data sheet. So there will be a graph where the rotation speed will be given and what will be the expected thickness that is given. So you can find that, and you can use use the desired. So what is the desired thickness for you? You can use that respective rotation speed to get that thickness. Okay. And then in case of biomems or biological sensor, how SU8 is used. SU8 wells are used in drug screening, diagnostics, and other MEMS based. Where you need some transparent but stable structure. Okay, MEMS based biological and biomedical application. Okay. So these are about biomedical and biological applications. We talked about drug screening and diagnostics, how we can find the efficiency of a drugs using MEMS sensor. Okay, what are some other application of MEMS sensor? So what were the examples given? So MEMS sensors are used in case of automobiles. Okay, this was discussed in the class. What are different types of MEMS sensors in automobiles that you can search? One example can be a gas sensor, MEMS based gas sensor. Okay, there will be some pressure sensor. So you know that nowadays the different cars will cars in their design, many safety precautions are integrated in the design. So there will be different types of sensors used for that, and many of the sensors can be MEMS based sensor. So you can look like what are the sensors. Those are of MEMS based sensors used in automobiles. Okay, my handwriting is not that good in this tab. I hope you understand. Okay, now what can be other example of MEMS based sensor? So there may be some RF sensor, radio frequency sensors where some radio frequency switches are used. So those switches can be RF MEMS switches. Okay, that is a different topic of discussion, different topic of research, and altogether RF MEMS switches. So those switches can be used in sensors or in other applications. Okay, so RF MEMS switches which are normally used in case of communication, in RF communication. Okay, what is RF? Radio frequency. You know that we use different frequency bands for communication. So the switches are used in uh, those frequencies. Okay, and so we cannot use like a normal switch many times in those frequencies. So in us, and also suppose we want to make smaller devices, um, uh, we don't want a very bulky electronics, then we can go for small MEMS sensor, which can basically either transmit or block RF signal, radio frequency signal. Okay, so this is not directly a sensor, but these components can be used in case of sensing as well. Now, towards the end of the theory videos for this week, the professor has discussed few key points about MEMS, and I think you should remember these points after all these weeks of discussion. So I will note it down. Okay. Uh, this is for your reference so that you can remember later. I am sure that you have gone through the lecture videos and already know this. Okay. So we have already discussed MEMS have four components: microelectronics, microsensors, microactuators, and microstructures. Okay. So MEMS system are made up of microsensors. We know what is what the sensors, like microsensors, sensors in micro dimensions, and then micro actuators. So what are actuators? Actuators will actually move some parts in our MEMS system. Okay. Microelectronics, that is basically like the brain of your MEMS system, that will make decision. And microstructures. Okay, microstructures can be like some additional components like channels, some diaphragm, cantilevers, all those components. Okay. Next point is fabrication of the sensor is very important. That is a different topic altogether, because making this type of structures in this small dimensions is not always easy. There will be some suspended structures, some a very thin structure. So we will do the etching, bulk portion of the etching, so it is not always easy. We'll go for surface micro machining. There some problems comes there also. Sometimes it is not easy to make a suspended structure in using surface micro machining. So all those fabrication difficulties come, but basically how we do tackle these problems, we'll go for few techniques, which are deposition, lithography, and etching. Okay. Fabrication involves deposition, then patterning. Even if you want to make a very simple like a resistive sensor also, you should go for patterning, because you will need some electrodes to your sensing material. Okay. So patterning or lithography is like the heart of microfabrication, that will need multiple times, like as I have given you some examples, that multiple steps of lithography is required. Okay. Another key point was that chemical etching is more popular because of the higher etching rate. I mentioned earlier also that there are chemical etching techniques and physical etching techniques. Chemical etching is wet etching, physical etching is dry etching. Usually chemical etching is faster, the etch rate is more, whereas dry etching is slower, but you will get a better controllability, like the dimensions will be shape of the structure will be uh, as you want many cases, because the etch rate is slow, plus the etching will be directional, whereas chemical etching will be isotropic. Okay, it will be same in all directions. And also because of the etch rate is high, if you want to etch a very thin layer, then it is not like a good option. But the selectivity in chemical etching is good. We know that buffered hydrofluoric acid will etch SiO2, not other material, uh, normally used material in our fabrication. Also, KOH will etch silicon, not other things, so other materials. So selectivity is good for chemical etching. And why we prefer chemical etching in MEMS, because many times we go for bulk micro machining, where we have to remove bulk portion of the silicon substrate, and in that case we usually need the higher etching rates, and chemical etching gives that. Okay. Due to its high etch rate. Okay. And then we discussed about three different types of sensors, like basic sensing mechanism for pressure sensor, because we make in MEMS sensor we make suspended structures, so these are for pressure sensing. And there are three different types of pressure sensors: capacitive, piezoelectric, and thermal. Okay, piezoelectric and piezoresistive also in similar category. These are like different working mechanism, you can say. Piezoelectric and thermal. And then we discussed about earlier classes, we have discussed about three different types of actuators. So what are those? Thermal, that uses thermal expansion of material. Capacitive, and piezoelectric. You can think about different examples of this kind of sensors and actuators. Okay. And then last point was why I mentioned that the fabrication can be complex for MEMS sensor, but still we go for MEMS because there are certain advantages. What are those advantages? So because these are very small sizes, the speed is the the size itself is a good advantage, because we can integrate many more sensors together, okay, in a small or limited area and volume. And then also the power consumption is less because of the size of the sensor, these are very small. And then the speed of the sensors are usually very high compared to like a bulky device or bulky sensor. Okay, so the benefits: speed, size, power consumption, And you can think of other advantages of sensor also. That is, I'm leaving up to you. Okay, I hope that these notes will be useful to you. I'll take a pause. If there is any question, you can ask me or write in the chat box. So these are mostly the topics those we covered in the lecture videos. If there is no question, I will go to the next slide. So there were few lab classes in this week. So these are like in few lab classes, Arduino board where that was introduced. So you already know what is an Arduino board. I'll not go into the details of these things. These are few notes that I have prepared for this session. So this is one Arduino Uno board you can see here. So you can see Arduino is written and this board is Uno. It's my cursor. Okay. So this is Uno. Basically it has an microprocessor, microcontroller IC, and as I think in first or second week classes I discussed that in a sensor system we basically have three components. We have sensors, then we have a decision making unit, which will take the sensor output as input. So whatever the sensor senses, that will be sent, that data will be sent to the decision making unit, which will be like a microcontroller, and there can be other peripheral components also. And that decision making unit will take some decision based on the sensor output, and that will be that the output of the decision making unit will be sent to the actuators as an input, and based on the decision, actuators will act on something, right? This is like a basic block diagram of a sensor system. So when so there are like two parts. Either you maybe you are working on sensors, like the design and fabrication part of the sensor, or maybe you are working with interfacing those sensor with circuit or real world. So you know that in IoTs, Internet of Things, many sensors are used, not like one type of sensor. So if you want to make a sensor system for smartphone, or say for smart window, that will like open or close automatically depending on like what time of the day. So if you want to make those kind of sensors, or if you want to make like a smart lighting system, so if the ambient light is low, you want your system to your sensor to sense that the light information, and then to turn on or off a light. So all maybe some of you are working in this component also, like the interfacing part. In this course, so both of this component are discussed. So as you have seen that some lab classes were like in some lab classes, Arduino board, or basically the interface and circuit part, was introduced in this week. So Arduino is like open source hardware and software. It is used in many electronic projects. I have used in my BTech days, because these are open source software. You can buy an Arduino board in Amazon or any other site. Okay, these are very easily available. There are different types of Arduino boards. Uno is the one that I had, was Uno, and there is Nano also, but the size will be maybe smaller, like much smaller than the Uno board. And there is Arduino Mega and Arduino Micro. All these boards are so, like, Uno is very popular. And if you want to make like the one that I mentioned, like if you want to make a smart home this kind of project. Maybe some of you have already done in your undergrad course also as an assignment. So you can make this very easily using an Arduino board, and you need few components whatever you want to do, and few jumper wires to connect with all different pins of the Arduino. And because it is an open source hardware and software, many like you will find many videos, many articles, many blogs that will be helpful. Like you can find help very easily if you want to make an Arduino project. Okay. The programming language here is similar to C or C++. If you know C and C++, then it will be very easy. At the end of the day, the programming is like logic. You should think like, if you can think like what will be the like sequence of work, then you can easily make it into a code in Arduino environment, like open source integrated development environment, Arduino IDE that is available. You can download it easily, you can write the code and then run it in Arduino. Okay. Then one lab class was on PDMS molding, how PDMS molding is done. That is like the video is self-explanatory. I will not go into the details again. You can I hope that you have already watched our videos, and how we can make the PDMS mold we discussed in last week also, like theoretically, and it was discussed, like it was shown to you experimentally in the lab videos also. Okay. Next I will go to the questions. If there is no question, then I'll start the questions. So this first question is from the last week actually, but I wanted to discuss about it, so I'll write down the question first. So which biosafety, so this was discussed earlier, I hope that you remember, which biosafety cabinet provides protection only for personnel, I mean the person who is conducting the experiment, who is doing the experiment, but in the environment also, the lab environment, but not to the product. Product means the like the sample that you are using, or any other equipments or other things that you are using. Okay. Basically there is a possibility that contamination may happen to your sample, or to your device, or whatever product that you are actually tasting. So what the options are, so you know the there are different classes of biosafety cabinet. So option A is class 1, B is, so there are 3 classes basically, so these options are given in class 3. There is like subcategory between these classes also. I'll not go into that. Also I'm not very aware of that also, but different classes were discussed, so that is why I'm giving you the option as class 1, 2 or 3. So in which category, in which biosafety cabinet provides protection only for personnel, that is the person who is doing the experiment, and the environment, the lab environment, so that no hazardous gas or chemical is released to the environment, but it does not protect the product, the sample or the device that you are tasting. Okay, so you can write down the answer in the chat box. I will take a pause here. Is there any answer? Some people have left, I guess. Okay, someone has given the key properties of SU weight. Yes, like the all these points that you have mentioned are true. I have already discussed, and thank you for giving like a good summary for everyone. Okay, class 2, the answer is so if the actually the answer is class 1. If you remember, it was discussed in the so the TA mentioned in the lab video is that, so what happens, there are three types of biosafety cabinets where you will do your experiments, tasting and analysis, like of your biological sample or biomedical sensor that you are designing. Now, what are the difference in case of class 1? What happens? It basically protects the person and the environment, but not the product. How? So what happens is that that cabinet, in that hood, the air from environment actually goes inside without like going through any filter. Okay, so if there is any hazardous chemical or any like gas that can deteriorate this product, because we are working with biological samples, so there may be maybe it should not be exposed to like a normal environment. So if there is certain gases or certain chemicals in air, normal air, so that will go inside the hood. But what it does is that in case of class 1 cabinet, it actually filters the inside air before releasing it. Okay, that is a filter. So it will release the air uh, from inside the chemical. So if your biological sample has some it is something like you will get infected from that. Okay, so that sample is like that, then you will not get infected because you are using a hood, biosafety hood, and it will actually filter the air before releasing it. Okay, that is why, that is what class 1 biosafety hood does. In case of class 2 and 3, it actually filters the air before entering inside the hood also, so that actually protects the product as well. And the difference lies like there are different subcategories also, like what it does, some portion of the air will be recirculated inside the hood, and some portion will be released after filtration, and based on how much, what are the portion that will be recirculate inside the hood, and what will portion will be filtered and exhausted from the hood, based on that other categories are defined. So in those categories in class 2 and 3, the product is also like kept in mind that there is no contamination to the product, the sample that you are testing, or the device you are testing. Okay, so for this question the correct answer is class 1. So I'll write it down. Okay, A, class 1. The reason is that it protects the user. So in any biosafety hood, it should protect the, it usually protects the user and the environment, okay, and the environment by pulling air inward. So it will not throw air outside directly, okay, and filtering it before release. That is how it protects the environment also. However, it does not protect the product that is your sample or device because unfiltered air goes inside. Okay, so this is the first question. Let's go to the second question. Okay, so I have already written. So we've discussed about impedance sensors and how it can be used for drug screening. Okay, now in impedance sensor, what we have basically, we have an interdigitated electrode. What is an interdigitated electrode? This is like a comb like structure. So these are metal lines and there are other metal lines also. Okay, so this is an interdigitated electrode. This kind of structure electrode is used in case of impedance sensor. So what is the advantage? So we know that if you know that if you want to measure the resistance of say some material, you can just connect to electrode and directly measure. Similarly, you can connect two probes, two electrodes, and then you can measure impedance. It's similar, but instead of that we go for interdigitated electrodes. Okay, what are the advantages it's provide? I've already mentioned briefly. You can you can recall and you can add few to whatever I said and write in the chat box. I'll take a pause here. Right here, what are the advantages of interdigitated electrodes in impedance? Okay. So this is a question. You can name few. you can think it in terms of biomedical sensing or biological sensing also. Like there are different ways you can do biological sensing, but if you want to do impedance sensing, so what will be the advantage compared to other techniques those are available for uh, biological sensing? One, I can tell you that in many of those sensors, in other biological sensors, different kinds of fluorescent dyes or like coloring material is used, say some nanoparticle that shows color. So what will be the advantage instead of those type of sensor if you use an impedance sensor? Okay, that can be an advantage also. No answer? Okay, if not, I will write down few. Okay. So as you can see here, if you use an interdigitated electrode, the overall sensing area will increase. So say if you if you place some material here, okay, because of these two electrodes, so you know that there will be some capacitance between these two because these are metal lines. There will be some capacitance. Okay. Now, if the capacitance will depend on the material between these electrodes. Okay, between these metal lines. Now, if the material is different, if you are placing something and somehow the properties of this material is changing, then also this capacitance will change and the overall impedance of the sensor will change. Okay, so basically it provides a larger effective sensing area. That is why we go for this kind of interdigitated structure, comb like structure. Okay, that is one advantage. IDs provide a large effective sensing area in a compact design. This is also important because you have multiple cones, multiple metal lines, so the overall structure is very compact. Okay. Now, there will be there can be multiple advantages. Like I mentioned, I will give you a few. One example that one advantage that I mentioned, that in many cases, because we are discussing it in context of biological sensing or biomedical sensing, so what in other type of sensing, sometimes different fluorescent dyes are used, different specific chemicals are used, uh, that gives a signature of a particular material in the sample. Okay, say if the color of this liquid will change to a certain color, then it will indicate that certain chemical is present in the sample, something like that. Okay. If you go for another type of sensing, so this is one type of sensing mechanism, okay, based on fluorescent dyes or other chemical, based on other coloring chemical or color that provides some visual information. Okay. Now, instead of that, if you go for interdigitated electrodes, then um, what advantage it's provided that you don't need extra like chemical for that. Many times these dyes and these materials, these chemicals are expensive, and what you can do, because it is an impedance sensor, you can easily make using like a standard fabrication process. You can replicate it very easily. Okay, if you use soft lithography, then you can make it very easily in a very less amount of time, and you can reuse these sensors. Okay, unless other different, like in some type of sensing mechanism the sensors are not reusable, but you can reuse these sensors like again. If you remove the sample on top of this interdigitated electrode like properly, because these are metal lines, so it will not go away that easily. If you can clean properly, then you can reuse again. Okay, so this is one very like important advantage that actually reduces cost. So I'll write it here. It allows real time label free means those dyes, those like signature chemical that you use, that you don't need to use. That is what it means by label free. Monitoring of biological samples without the need of uh, fluorescent okay, so the spelling is not right. Fluorescent dyes or chemical marker. So these chemicals are normally these are called as chemical marker, that will mark the presence of some disease or some component in that sample. Okay. Okay. Generally this provides visual information, so these are normally colored due to some reaction will happen between the sample, the component, the analyte that you want to detect, with some other chemical that actually carries these chemical markers. Okay. So these are few advantages. There will be like because of interdigitated electrodes, if you are using it for biological sensing, so the cell adhesion will be better, so the material will it will be easier to detect those samples. the 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 analyte that you want to detect, that will stick into your substrate better because of this kind of structure. Okay, that will sit properly, and all those advantages that it can provide. But the main, these are the main advantages, that it provides larger effective sensing area, and it provides level free monitoring for biological sensing. I hope it is clear. Is there any question? Large sensing area enhances interaction with analyte. Yes, because we are considering in terms of biological samples, so that is where I mentioned. Yes, even the small change in case of interdigitated electrodes also you can measure. Okay, it is compact in design because of the structure. Okay, low sample volume. Yeah, that is like what is important in case of biological sensing, because many times, as I mentioned earlier, also that sometimes you have limited amount of sample with you for sensing. Okay, because these are biological sensing, biological samples. Okay, so with the interdigital electrodes, even if you use a small amount, then as I shown you in the diagram, there will be some change in the capacitance or overall impedance that can be measured and that can be sensed. Okay, easy fabrication. Yeah, it is easy because we already have developed the photolithography process and etching and how we can make interdigital electrodes on top of different substrate. Everything is already well known. That is why it is easy to make. Okay. All right. Let's go to the next question. So as I mentioned that there are like two ends in the spectrum. Either you are working in design, you can work in design of a sensor, like how we can improve the reference sensor characteristics, and the other end it how you can integrate your sensor to a system. Okay, so basically in IoTs, Internet of Things. Okay, this question is on that. What is the primary advantage of MEMS based sensor, or you can say micro sensors, okay, in IoTs compared to other type of sensors? The options are better accuracy, miniaturization, and low power. C is more sensitivity. So the question is, what is the primary advantage? Okay, uh, there can be other advantages like from the options, but what is the primary advantages? I've given you three options. You can write down the correct answer in the chat box. So you all know what IoT is, Internet of Things means. So you can think about the answer in terms like how IoT, like what is IoT and how it works. So in IoTs, So this is Internet of Things, right? In IoTs, many sensors are involved, not only one type of sensor or one sensor. Okay? So you can keep that in mind and think like what is the answer. So do I have an answer? Answer B. Yes, answer B is the correct answer because we are talking about IoTs where many sensors are used, many different types of sensors are used. Okay, basically, in like it's a network of different sensors. Okay, so BEM sensor can provide better accuracy or more sensitivity based on the design, but the main advantage is miniaturization and low power consumption. Okay, why low power consumption? Because these are very small in size, so they require very less power for operation. Okay, I'll write it here. MEMS sensors are very small in size, thus require low power. This makes them uh, them suitable for IoTs and can be for uh, portable devices, for portable sensors also. Okay, you know that many sensors are used in IoTs, right? If you calculate the power consumption of one sensor and then multiply with, let's say, hundreds of sensors are used in one system, so you, even though one sensor is not consuming much power, overall the system is consuming a lot of power. Okay? So that is why the lower power consumption, lower the power is always better. Okay, that is why MEM sensors or micro sensors are used. Also, it will be compact in design when many sensors are used. If those are in micro dimensions, so this is not like an advantage of MEMS sensor. If you like a micro electromechanical sensor, that maybe some no mechanical component, but even if you are designing a sensor in a very small dimension and in micro and nano dimension, that will be useful in case of IoTs. Okay, let's go to the next question. This is a very straightforward question. How does an Arduino read digital sensor inputs? I have mentioned you, I have told you that I'll not go into the details of what was discussed in the lab classes, but I will ask you a few questions. So uh, let me know in the chat box what is the function that is used to read a digital sensor input in Arduino. Okay, or you can say any digital data. Now I don't know what you can easily Google because I'm not seeing you, but I hope that you actually remember it and you can write the function in the chat box without looking. How to read digital data in Arduino? That is the question. From digital input pins, yes, we will read the data from digital input pins, but I'm asking what is the function to read digital input data. If you can recall, there are different functions: how to initialize serial monitor, how to provide delay. So they are already in the Arduino libraries. These functions are written. You just have to call the functions. If you know C and C++, it is easy for you. That like you do something called function call. Okay, the function is written in the library. You just call it and use it. So what is a function? Function is like a set of codes that is written to do a specific work, right? So there is a certain function that basically reads digital input data in Arduino. So what is that function? There are different functions to read digital digital input data and analog input data, and then you can write digital data in some data points, so which will be like an output to an actuators. Okay, so turning on and off an LED, turning on and off a stepper motor. If you are controlling using a digital pin, then you will like write some function like digital write to change the state of that pin from high to low. Okay, similarly, what is the function that is used to read a digital data? Whether the input, whether the that pin is in high position or in low position. Suppose you have a sensor that provides you like two state. Okay, digital okay, digital input. So see, you can go to the Arduino website, and there is like many resources available online. So I'll give you digital read. Yeah, that is the correct answer. And when you write the function, when you write a function, then you should also use that bracket. Okay, if you know C++, you know why you use the bracket. Okay, I will write it here. So I'm writing a few of the functions. Those are used in Arduino. In the meantime, you can tell me in the chat box that do you know C or C++? Okay, all of you. Like there are mainly maybe 5-6 people in the meeting. All of you can write whether you know even like a basics of C or C++. Then it will be very easy to write code in Arduino. Okay. If not, then also it is easy because lot of help is available for Arduino. Like there are many tutorials. You can see that. Like I have bookmarked few here. You can see like controlling Arduino. I don't even remember what was the actual tutorial here. Search in YouTube, you will find a lot. Okay, not much, but some basics I know. Yeah, basics will do, because in many times we don't write all the code in Arduino because many of the functions are already written. We use different libraries basically. Okay, whatever, like there are many libraries. You can just install Arduino IDE once in your laptop. Even if you don't have a Arduino board, you can look like what are different libraries available, what are different functions, like examples are also given. You can check like, okay, whether you will be able to understand or not. So I will write few functions which will be used when you interface a sensor with an Arduino board, okay, or an actuator like a stepper motor with an Arduino board. Okay. So first function is digital read. So it is written here. You should know. You should be careful with the like capital and the case of the letter, like whether it is in capital or in lowercase. Digital read. Okay, this is a function. A function to read high. So you can use your serial monitor to see what is the value. If you write your pin number here, say pin 1 you are using as a, like a input pin, and you are using digital read function, then in the serial monitor you will see whether it reads high or low. Okay, whether the value is high or low. So when you will use this digital read, so when you have an input, like a input pin, okay, from where you will get the data. So suppose you are interfacing a sensor, the sensor output is either high or low, and you are reading that data. So it's not like you are connecting your actuator and using digital read. Okay, you can do that, but it does not mean anything. Okay, so you will use this with input pin. Okay, to read, I'll give you an example. Read signals from, say, digital sensor. What can be a digital sensor? It can be an IR sensor. Okay, it can be like a button or something, like simply a button. It can be a sensor. Okay, like some switch. Okay. This is to be used with sensor or with input pin. Okay. Next, similarly, we will have analog read. Okay, if your sensor is analog, you will write your pin number here. Okay, function to read analog input. Okay, so it what it does, it provides your input. It will give you input, but how it will give? So it will return a value. In serial monitor you can see the value. It returns a value in the range 0 to 1023. Okay, so basically 1024 values, between 1024 values one value will be returned. Okay, so this is analog read. Okay, so you can see that this is also like a digital number. So basically there is a 10-bit analog to digital converter is there, but it's an analog read, analog input signal. Okay, instead of only high and low state. Okay, then if you have an actuator, if you want to change the state of some pin, how you will do? You will use some function called analog write or digital write. So for digital it will be digital write. So all these functions, how digital write, or what is inside analog read or digital read, digital write, all these are available in the library. We don't have to like actually write a code, we just have to call this function. Okay, digital write, what is the like syntax? You will write a pin number. Okay, and you will provide either high or low, like whatever you want to do. You will write here, you will give the pin number, you will give the pin number here also, here also. Pin number, you can like, it can be you know what are different digital pins. There are few digital pins available in the Arduino board, there are few analog pins. Okay, you will give the pin and what is the state you want to write. Okay, this is the syntax. what it does, it sets a digital, okay, pin to high. High means it will provide say 5 volt from the Arduino, or low is 0 volt. Okay, if you provide 5 volt say to the positive terminal of an like an LED or diode, so it will be on, and if you provide 0 volt then it will be off. So this you connect with an actuator, so maybe like a switch that will just turn on and off something, a light say. Okay, then what you also use analog, right? Again, pin and your input, not input, like value, whatever value you want to give, like the analog value. Again, you cannot give like a very random number like 2.56 volt, something like that. So what it does, it generates PWM signal. Okay, not like a completely analog signal. What is PWM? Pulse width modulated signal. So which is like which is similar, which is like an analog signal. Okay, it provides analog like voltage, analog light, not exactly analog, voltage. Okay, so there are few pins, you can check which are the pins, those are for analog, right? Which are the PWM pins, and the values can be between 0, which will give 0 volt, to 255, which is the 5 volt maximum, and there will be like 256 values from 0 to 225. Okay, total. Again, it's like analog to digital, digital to analog conversion. So you already know, if you are from electronics background, what is analog to digital and digital to analog conversion. Okay, so it's like an analog signal, analog voltage, but not exactly analog, it's a PWM signal. Suppose where you can use, the example that was shown in the lab class was the speed of the stepper motor, right? You can also control the brightness of some LEDs, say, using this kind of analog write function. Okay, so these two you use with your actuators, these two you use with your sensors. Okay, these are for input, these are for output. Okay. It's clear. If you really want to know, then you can practice Arduino, like you can download it and practice. In the final exam, so in the final exam, see, I'm not sure, the questions, so these are I have prepared for this is for your, like few questions are for solving the assignments, and few questions are like whatever I thought that these are useful, that's how I included. But you can check the assignments question. Exam, I hope that in exam, I think that in exam the questions will be like that. Okay, the assignment question, it will not be like a programming question, like a programming session, because that is not useful, right, in a pen and paper exam, because you are not anyway doing this kind of programming in the exam. Okay, okay, for about the exam pattern, so I'm not the right person, you can ask in the discussion forum, the information will be available there. Okay, and before the exam also, I think there will be some announcement, you can check. like exam related questions, so I'm not the right person. Like I'm mainly handling this live sessions, and I'll later like I want you to know that this is part of my PMRFTA duty. So I'm mainly focusing on like the lecture videos which are like the topics those were discussed and some problem solving. So when I like as I mentioned earlier also, the problem solving sessions are for solving questions. Those will be helpful for your assignments, but like other kind of details I'm not aware, you can ask in the discussion forum. Okay, so I can check the assignments here. Have you gone through the quiz or assignments? So you can see the small questions are given. So this is not like a coding question, but it's on Arduino. So you can expect this kind of questions also. Okay, so this is the next week. I don't know what was covered in the next week. Okay. How many of like these are like this? Should I go through the full library? So you will not be. I don't think you'll be able to complete the full library. So there is no need. Like you just the functions that I mentioned. So I feel like those are. I cannot say those are enough, but for a basic understanding how to interface Arduino board with a sensor and actuator. So I think these functions are like I cannot say again enough, but those are useful. Okay, and programming question, you will not be asked to do like a programming, because how you can actually verify it. Okay, but again for clarification you can ask in the discussion forum what will be what kind of question you can expect from the lab session. Okay, here I have just given you just so that you can actually remember this, and I think that this is useful for you, and that is why I have taken this question. Okay, yeah, and don't get scared of programming. Okay, it's this is a course for sensors and actuators, not for C and C++. So you will be expected, so you are expected to know the contents of sensors and actuators, not some programming language. Next I will take one more question. This is on PDMS molding. Why is degaussing, you have watched the video of PDMS molding, right? So why is degaussing an important step in PDMS molding? Okay, so I think you can answer it. I will not give you options for this. Okay, if you have watched the videos you will be able to answer. So why degaussing is important in PDMS molding? Okay, to remove the air bubble, and why we remove the air bubble? Okay, because if you do the curing with the air bubble, then there will be some defects. So there will be like bubble, like okay, there will be defects, there may be cracks. Okay, so that is why degaussing is very very important, so that there is no air bubble inside your solution. It's not solution, but yeah. The answer is to remove trapped air bubbles that could create defect. Okay. So you already know how the gassing is done using a desiccator. Okay, okay, because we do not want any defect here. There can be defect, there will be cracks if we don't degas it properly. Okay, that is why we go for degassing. Okay, this is one important step in PDMS molding. So that's all. It's already time, so I have 5 minutes. If you have any question, then you can ask. If you have any suggestion, feedback also regarding the live session, also you can tell me. Okay. I have mentioned earlier also I cannot see your faces, or this is in online mode, so uh, I am hoping that the sessions are useful for you. Okay. If not, if there is any suggestion, there is any comment, you can tell me, or if you have any doubt in this week content, also you can ask. I'll stop the not recording, sharing. Yes. Okay, thank you, Priya. I hope the session is useful. Okay. Thank you. So if there is no question, then I can stop. See you in the next week with the week 5 content and few questions. I request all of you to watch the lecture videos, classes before coming to the live session, and I'll try to focus more on questions from the next week onwards. But again, I'll give a brief overview of the topics, okay, as well. So I do it mainly so that everyone is on the same page, and try to give you as a summary so that it will be with you. I hope that you are able to access, you can access these notes that I provide in the NPTEL portal, and that will be for your reference. Okay, thank you everyone. See you in the next week.